So why does a $100 million aircraft, main engines shut down, keep something else running? Right now, a parked airliner with its engines off is still burning roughly 40 gallons of jet fuel per hour, feeding a second turbine hidden in its tail. Scale that across the tens of thousands of turnarounds happening worldwide at any given hour, and you get a staggering amount of fuel burned by planes going absolutely nowhere. But what sounds like pure waste is actually the product of a calculation most passengers never see. Inside this story is a mini jet engine whose entire job is to prevent a second start of the main engines, a form of engine damage completely unrelated to mileage. A regulator is now pushing airlines to shut down within minutes of landing, and an industry is quietly balancing the cost of idling against something far worse, the risk of an aircraft going cold and dark with passengers still on board. That balance starts with a machine most people have never heard of. The machine housed inside the tail cone is the Auxiliary Power Unit, or APU. On narrow-body airliners like the Boeing 737 and Airbus A320, this is typically a Honeywell GTCP-131-9 gas turbine. It is fundamentally a miniature jet engine, but instead of producing thrust to push the aircraft forward, it spins a shaft connected to an electrical generator and a heavy-duty air compressor. When the main engines are shut down at the gate, the APU becomes the primary lifeline for the aircraft. It generates the electricity needed to keep the flight deck avionics active, the cabin lights on, and the galley systems functioning. Simultaneously, it produces high-pressure bleed air. This compressed air is piped directly into the environmental control system to heat or cool the cabin before passengers board, and to run pre-flight pressurization checks. Most importantly, this compressed air provides the high-velocity pneumatic force required to spin the starter motors on the main turbofans when it is time to depart. Think of the APU as the airplane's self-contained hotel generator. The fuel cost of running this system varies heavily, depending on the electrical and pneumatic demand. In a static state with the cabin air conditioning turned off, a Honeywell 131-9 burns as little as 1.5 gallons of jet fuel per hour. But once the crew switches on the air conditioning packs to fight ambient heat, the load compressor must work at maximum capacity. This pneumatic demand drives fuel consumption up to 30 or 40 gallons per hour, representing roughly 2% of the aircraft's total hourly consumption. If the aircraft is parked at a modern terminal, why must it rely on its own internal turbine for these basic needs? Why can't ground crews simply plug the airplane into the airport's electrical grid and use terminal-supplied air conditioning? A jet engine startup differs fundamentally from starting a car. It is a severe thermodynamic event. When an engine sits at the gate, its internal components cool down to the ambient air temperature. Upon ignition, fuel is sprayed into the combustor, and within seconds, the high-pressure turbine blades and combustor liners are subjected to a temperature jump from ambient to over 1,000 degrees Celsius. This sudden uneven heating causes the metal components to expand at different rates. The outer skin of a turbine blade heats up rapidly while its cooler core lags behind, creating immense physical stress. This process drives thermomechanical fatigue. Over hundreds of start-stop cycles, this repeated thermal expansion and contraction microfractures the nickel-based superalloys. It is the primary cause of damage in the engine's hot section. Because of this, aviation regulators and manufacturers track engine wear using both flight hours and start-stop cycles. In gas turbine engineering, maintenance planning relies on a concept called equivalent operating hours. Under this framework, every startup is assigned a penalty factor that converts the physical damage of that single thermal shock into a corresponding number of steady-state running hours. While a typical start under standard conditions is weighted by manufacturers as equivalent to 3 to 5 hours of normal flight, a true cold start under demanding conditions can be far more punishing. For high-performance turbofans operating aggressive short-haul schedules, some operational models show that a single cold start can subject the high-pressure turbine to a fatigue load equivalent to 100 to 200 hours of continuous steady-state cruise. The mechanical toll of an entire transatlantic flight can be compressed into those first few violent seconds of ignition. Under Federal Aviation Administration guidelines, critical rotating components, known as life-limited parts, must be retired and replaced once they reach their certified cycle limit, regardless of their physical appearance. A set of high-pressure turbine discs or blades might only be rated for 3,000 starts before mandatory disposal. Since a complete hot section overhaul can easily cost millions of dollars, minimizing the total number of start-stop cycles is a primary economic objective for fleet managers. This reveals the counterintuitive reality of aviation maintenance. Keeping the auxiliary power unit running to delay starting the main engines is a deliberate choice to protect the hardware. An engine spared a single cold start may have burned extra fuel on the ground, but it preserved a far more expensive mechanical lifespan in the process. What happens when these engineering equations meet the chaotic reality of a busy airport ramp? While the physics of thermal fatigue dictate long-term maintenance costs, the immediate choice to keep a turbine spinning on the ground often comes down to the unpredictable nature of airport infrastructure. Modern terminals are designed to supply parked aircraft with electricity and air conditioning directly from the gate, theoretically allowing the plane to shut down completely. But theory often clashes with physical reality. Ground crews must rapidly align passenger bridges, drag heavy electrical cables, and hook up high-pressure air hoses. If any link in this physical chain fails, or if the gate's local grid experiences a momentary power surge, the aircraft's primary systems can drop offline instantly. At older airport terminals, remote parking stands, or during peak traffic hours, ground support infrastructure is notoriously prone to failure. Fixed electrical ground power units and preconditioned air carts frequently malfunction under heavy demand. A loose power connection or a sudden drop in compressor pressure can instantly sever a parked plane's access to terminal power. In a tightly scheduled network, short-haul turnarounds are compressed into strict 35 to 45-minute windows. If a flight crew plugs into an unverified gate connection and completely shuts down the aircraft, they risk going fully cold and dark without a backup. Rebooting a modern flight deck's avionics, reestablishing cabin climate control, and waiting for ground technicians to troubleshoot a dead cable can easily trigger a 20-minute delay. Under the Department of Transportation's strict tarmac delay rules, those minutes carry heavy financial penalties and compound scheduling disruptions across an airline's entire system. Consequently, flight crews and dispatchers treat the onboard turbine as a vital operational safety net rather than a wasteful luxury. In some extreme cold weather or high-altitude environments, the risk of a failed ground handoff is so high that some airlines authorize a different procedure entirely. Instead of shutting down both main engines and risking a complete system shutdown on a questionable gate hookup, crews will keep one of the massive wing-mounted turbofans running at idle during the entire turnaround. While this practice burns significantly more fuel, maintaining a trusted onboard power source remains the most reliable path to an on-time departure. Behind every parked airliner lies an invisible calculation performed at the operations desk. This is where fuel burn and emissions are balanced directly against hardware wear and scheduling risk. While no single universal cost model is publicly standard across the industry, the math remains remarkably consistent. On one side of the ledger is the baseline cost of running the auxiliary power unit, typically 30 to 40 gallons of fuel per hour, plus $40 to $50 per cycle for routine upkeep. On the other side is the far greater penalty of a main engine start-stop cycle, which rapidly consumes a turbine's certified limit of 3,000 starts. Yet the most volatile variable in this equation is not mechanical, it is operational. Delay and cancellation risks belong to the very same calculation. If an aircraft shuts down completely to conserve fuel and unreliable ground infrastructure fails to support the restart, the resulting departure delay can trigger cascading disruptions across an entire flight network. For decades, the economic logic has favored keeping a turbine running because a failed turnaround is almost always more expensive than the additional fuel burn. For airlines, burning fuel on the ground is simply the price of operational insurance. This long-standing economic calculus is facing unprecedented pressure from regulators and airport planners who are rewriting the ground rules. Under the California Air Resources Board's proposed statewide Clean Aviation Initiative, the freedom to run the tail turbine indefinitely is coming to an end. Draft rules target 2032 to enforce strict APU shutdown windows, requiring operators to turn off the auxiliary turbine within 5 minutes of arrival and limiting pre-departure use to between 15 and 45 minutes. This is paired with a broader mandate requiring all airport ground support equipment in the state to be completely zero emission by 2034. To make these limits physically possible, airports must dramatically scale up their gate infrastructure. Los Angeles International Airport has pledged to electrify its ground support equipment by 2033, though the precise percentage of gates fully equipped with high-capacity ground power and preconditioned air is still being finalized. The industry's major stakeholders, from airlines like United and Delta to manufacturers like Honeywell, are actively filing public comments to shape these looming rules. When environmental compliance becomes a matter of law, the old cost formulas collapse. Running a mini jet engine on the tarmac is transitioning from an operational choice to a regulatory impossibility. Three distinct technical paths are reshaping how aircraft manage power at the gate. The first relies on airport terminal infrastructure. By plugging into fixed electrical ground power, aircraft receive electricity at a steady 400 Hz, while auxiliary hoses pump preconditioned air directly into the cabin. This combination allows airlines to shut down the tail turbine completely without sacrificing instruments or passenger comfort. But what if the aircraft itself could be redesigned to limit this reliance? The second path alters the fundamental blueprint of the machine. The Boeing 787 Dreamliner uses a no-bleed, more electric architecture that replaces traditional pneumatic systems with electric starters and compressors, supported by dedicated ground power receptacles. This design relies on 6 onboard generators, 2 on each main engine rated at 250 kilovolt amperes, and 2 on the auxiliary power unit at 225 kilovolt amperes. By eliminating the heavy bleed air manifold, this electrical system reportedly extracts roughly 35% less horsepower from the main engines. The third path addresses the thousands of legacy short-haul aircraft already in service. For these fleets, Honeywell designed a high-efficiency mode retrofit for its standard 131-9B auxiliary power unit, which powers the majority of Boeing 737 and Airbus A320 fleets. This upgrade introduces a redesigned diffuser and autonomous software to regulate airflow. The retrofit reduces auxiliary turbine fuel burn and emissions by roughly 1 to 2%, saving about half a gallon of fuel per hour. It also extends on-wing life by up to 1,500 hours, showing how minor physical adjustments can alter the economic math of ground operations. On July 17, 2023, Delta Flight 555 sat on the tarmac at Las Vegas's Harry Reid International Airport as outside temperatures reached 114 degrees Fahrenheit. Inside the cabin, the AIR conditioning failed. For over 3 hours, passengers and flight attendants remained trapped in the rising heat, resulting in multiple heat-related illnesses, emergency hospitalizations, and a subsequent Department of Transportation investigation. The federal response to these ground events is severe. Under a DOT rule enforced since 2010, airlines face civil penalties of up to $27,500 per passenger for excessive tarmac delays. These liabilities accumulate rapidly. In 2023, the DOT assessed a record $4.1 million civil penalty against American Airlines for violations spanning from 2018 to 2021. When the consequence of a power failure is passenger hospitalization and millions of dollars in federal fines, relying on unstable gate connections is an unacceptable gamble. Keeping the tail turbine running is the safest, most conservative operational choice. The engineering designs pioneered by more electric platforms are expanding into new aircraft programs. Engineers are testing fuel cell auxiliary power units that run on hydrogen and air, generating electricity while emitting nothing but heat and water. This technology is already proven on the ground, where an estimated 300,000 refrigerated shipping trucks in the United States use hydrogen fuel cells to keep cargo cold without idling their main diesel engines, saving roughly 10 gallons of fuel per day per truck. Yet aviation moves slowly. The vast majority of passenger jets flying today still rely on traditional high-temperature bleed air turbines, and thousands of airport gates lack the high-voltage electrical connections needed to support a fully plug-in fleet. The industry is not abandoning its reliance on the tail turbine overnight. It is gradually shrinking, a necessary compromise. Today, the delicate balance between mechanical wear, safety, and fuel burn is facing its first major rewrite. As ground infrastructure modernizes and emissions regulations tighten, the operational math airlines have trusted for decades is changing. The mini-engine in the tail remains a brilliant compromise until the ground finally catches up to the sky. Subscribe for more deep engineering insights.